Hi guys, this is Emerald Out. Let's see what it is. A horizontal plane supports a stationary vertical cylinder of radius r and a disc A attached to the cylinder by a horizontal thread AB of length L0. So they have shown us the top view. There is a cylinder and there is this thread. At the end there is a disc, they have called it. And it is the length of the thread is given as L0. An initial velocity of V0 is imparted to the disc as shown in the figure. The time it moves along the plane till it strikes the cylinder is the time t equal to L0 square by x r0. So the x is clearly in terms of V0. As per dimension, and obviously more the speed, lesser will be the time. So we have to find how much V0 is that x. Friction is not there. So the first thing is to understand the question fully. If you don't understand the question, you won't be able to do it properly. So there is a cylinder which is, this is a side view, this is on a horizontal plane, and this cylinder is called stationary over here, rather I would call it as fixed. It is fixed, it can't move. You have a thread, one end is attached to the cylinder, the other end is free, having a disc that is called A. It is should be a point body, and it has got a velocity initially. That velocity is V0. So what is going to happen is this string, the black string what I have shown over here, is going to wrap around the cylinder. It is going to wrap around the cylinder, and ultimately the body is going to hit the cylinder after some time, and that time we have to find. So I think the best way to deal with it is to draw the top view. So I'll draw the top view. Initial V0 velocity and initial length is L0 of the string. Now we should imagine after a certain time t what is happening. So a certain amount of string would have wrapped on the cylinder, say this much is wrapped on the cylinder, and there I will take a tangent over here, and perhaps this much length is remaining. Roughly it seems, I'll draw a little less. So this much length is remaining, and it is going to further wrap. It would have a certain velocity over here. What should be this velocity? So I think it is pretty safe to imagine that the velocity, or the speed rather, would remain the same, because the motion is tangential to the force on it. At any given time the force is along the string and the motion is tangential to that, and that is a little bit of investigation and deep dive into the fact has to be, I mean, we have to cross verify that it is actually tangential enough to take it take the speed as same or not. So I will go towards the end of the problem, maybe I'll discuss this a bit more, that the speed is tangential to the string, and for now it seems like a very safe assumption. So how much is the time taken to travel? So we can have various approach. One is to get the trajectory, the whole trajectory, how the body was going. and the speed is constant, so the length of the trajectory divided by the speed will give you the time. We can look at this, investigate this instance and try to make some equation. So at this instance, say the string has already wrapped theta angle. So this arc length is your r theta. The remaining length will be your L0 minus r theta, and we can safely imagine that the body is in the next dt time going tangentially to this L0 minus r theta and would travel a certain angle. Say in dt time it travels a certain angle, and that angle is how it is related to this further wrapping on the cylinder. We can just have a close look at it into it. So if I have called this as theta, this is definitely d theta. So always d theta adds up to theta. So I can't mention a d theta over here directly unless until I verify that's also d theta. So this black line is a 90° on theta. This red line is a 90° on theta plus d theta. Hence the angle, you can check it in a closer way, in your own way. This angle is also d theta. Good for us. So the arc length which is travelled in the small time dt would be equal to L0 minus r theta into d theta. So that's the arc length which it travels. Now this is the point of rotation at that instance what we have taken. Even if you have a closer look into it, and you can always say that this length got reduced from L0 minus r theta to L0 minus r theta plus d theta. This length is L0 minus r theta plus d theta, right? But then there is this extra length over here which is r d theta. May not be a very straight line, but if we go into the details of it, the difference in the length of this and this would most probably come in d of something, d of some kind of length. So that is in order much lower than the r d theta or L d theta order. So we can safely assume that this arc length, the arc length over here, is equal to L0 minus r theta d theta. Again, it is advised that you go and look closely into this. It is always good that you also cross verify that is it okay in calculus to assume that or not. So clearly this length would be the speed into the time. So the equation what we can write is your v0 into dt is equal to L0 minus r theta into d theta. So the total time taken, this v0 is a constant, we can try integrating this. So the total time taken would be after integrating this. So we'll put an integral over here, v0 is a constant. So t times v0 is integral of this. So theta is, initially this theta is what? It is going from 0. Finally it will be what? The string would have wrapped around, and the arc length, say r phi would be the length of the string L naught. So it will go, the integration of theta will go from 0 to phi, L naught minus r theta into d theta, which is L naught theta minus r theta square by 2, putting the limits. We are going to get a L naught phi. I'll straight away put the phi value, so that is L naught by r. So L naught square by r minus r L naught square by r square. So 1 r gets cancelled. So L naught square by 2r. So that's your L naught square by 2r. Hence my t is L naught square by 2 v naught r. So in the question it is asked to compare with x. So your x is going to be 2 v naught. We can have alternate ways of doing it. Let me just quickly show you one. So I intend to get diagram is not coming very nicely. 1 second. So the body is going to wrap around and there is a certain trajectory it is going to follow, right? So if we can make the equation of this trajectory and find the length of the trajectory, so if there is any trajectory, what is the equation of the trajectory? The equation of the trajectory can be given as what's the length of the trajectory? The length of the trajectory, say this is the trajectory, this is your dx, this is your dy. So this length added, say ds integral, is the length of the whole trajectory. So your length of trajectory s is your integration of ds, which is integration of underscore of under root of dx square plus dy square. So if you are able to do this integration, you get the length of the trajectory. So many a times, like we know the dy by dx, we know the slope, so it can be written in slope. If we take dx common, this can be written as 1 plus dy by dx whole square times dx. We can also see that this ds is, suppose we know the slope and that angle is theta, then your ds can also be written as sec theta dx. So integration of sec theta dx. So let's apply that into this. So here clearly the slope, which is this angle, is related to this angle. So how are they related? If I make a flat line over here, if I continue this line over there, I'll rather show it on this end. So this angle is theta, so this is 90 minus theta, that being 90, so this angle is theta again. So if this angle is theta, then this angle is theta, and if that angle is theta, then this angle is your 90 minus theta. So the slope is of this trajectory, the slope is your 90 plus theta. So we can say the length of the curvature is equal to let me call it as S. S is equal to integration of sec of 90 plus theta into d theta. We are going to get the length into dx. So we are going to get the length. So depending on from which way we are taking our coordinates of x and all, if anything is negative, we can always make it as positive, the length as positive. So sec 90 plus theta is equal to a minus cosec theta. Cos in the second quadrant is negative, cos sine in second quadrant is positive. So we can write like this. If we are taking our, say, origin over here, then my dx is definitely negative, because my x will be a certain location x, and on increase of angle d theta, as theta increases, my x reduces. So dx, if d theta is positive, my dx is negative. So that way, hopefully this minus sign will be taken care of. So integration of this. So we have to integrate cosec theta dx. Now we have to write are either cosec theta in terms of x, or the dx in terms of d theta. So what is my x location? The x location looks pretty straightforward over here. It is so much of a length. I'll just clear it a bit. So it is so much of a length plus so much of a length. That's my x. So what is the blue length? The blue length is your r sine theta, and the red length is your this angle was theta again. So it is L0 minus r theta into cos theta. Yeah, so I'll just write my x is equal to r sine theta plus L0 minus r theta into cos theta. So let's check what is dx in terms of d theta. So we'll differentiate it. So r sine theta becomes r cos theta. L0 cos theta becomes a minus L0 sine theta, and a minus r theta cos theta gives us two things. So is a minus r cos theta when theta is differentiated, and it's a plus r theta sine theta when cos theta is differentiated. So yeah, good for us, few things are cancelling. So r cos theta and r cos theta gets cancelled. So what we are getting over here is our dx is equal to r theta minus L0 sine theta into d theta. Now r theta is definitely less than L naught, because the max of theta, which is phi, that time it is going to become L naught. So this is the negative term. So dx is coming negative when your d theta is positive. So no wonder, we have already seen that it should be that way. So the equation looks okay. Let us just substitute this dx into this. Good for us, everything is coming in theta format, so should be easy to integrate. So when we do that, so I'll do it over here. My ds integral, or my s, is equal to, I'll just take care of the minus straight away, and write dx as L naught minus r theta into sine theta is there, which gets cancelled with cos theta, and only d theta remains. So this is pretty much this kind of integration we were getting here also. Yeah, this was the length, exactly the same integration, and hence exactly the same answer. So you can further indulge, like further if you want to do, you can also do as you can write the whole y location as this much of the height plus this much of the height, which is here. Same way as we have given the x location, you can find the y location in terms of theta, and get your dy by d theta, so that you can write your this equation dx square plus dy square, or yeah, you can write this equation. You will eventually get the same thing, so you don't have to do that work. The sec theta dx is I think a decent way to verify that what we are doing or what we are getting is the right thing. So here, as I said, you should indulge a bit into understanding that can the speed be taken tangential to the string? We definitely know it is not purely tangential, but how much off it is from the real tangent, is it of any consequence in calculus, or it is not of any consequence? So what is the order in which it is off by? Is it in the order of the d, or it is d of d? So you have to check that for yourself. So that's it.